Okay, hello everyone, and thank you very much for having me here. So today I'm going to talk to you about some of the most recent results from our lab at Harvard, where we use these programmable arrays of Rydberg atoms to study some interesting quantum phenomena. So the general framework of our work is well described by this question: how can we take advantage of all the powerful properties of quantum mechanics in order to, on one side, learn new things about nature of phenomena, and on the other side, also develop new technology? So our work can be well described by these two categories of quantum simulation and quantum computation. And in the experiments that I'm going to show you today, I hope I will show you how we are hoping to contribute to these two fields. So in this context of quantum science, there are several platforms that are currently being used. And the one we chose is to build our quantum machine starting from individual neutral atoms. And the reason for that is that neutral atoms have a large number of properties that we believe are very useful in this context of developing a good quantum machine, as I'm going to show you in a second. So first of all, in my talk, I will tell you a little bit about the platform we use, which is these arrays of Rydberg atoms. And then I'm gonna tell you a little bit more in details about the latest experiment that we performed, which is related to the generation of quantum spin liquid states in this platform. And finally, I will show you how we can use this quantum spin liquid to do the first steps towards the creation and manipulation of a topological qubit. So let's start with the experimental platform. So the basic idea of our experiment is to start from a two-dimensional array of optical tweezers, which are simply these tightly focused laser beams, as you can see here, that we produce using a spatial line modulator, which allows us to generate arbitrary intensity array of laser lights. So we focus these beams at the center of a vacuum chamber, where we have a magneto-optical trap of rubidium atoms. And so when we shine this to the array of optical tweezers, we start loading the atoms into them. And here you see a few examples of different experimental repetitions where we have a random loading of atoms in these traps. Here I'm showing you an example for 600 traps. And so as you see, we have a random loading where about 60% of the traps are filled with a single atom. Another question is, can we rearrange these atoms in order to have an order array? For example, can we fill this subset of traps here? And to do that, we use a second set of traps, which are generated by acousto-optical deflectors, which allow us to have a second set of tweezers that we can move in the two-dimensional plane. And so these allow us to move the atoms towards some final target sites. So just to show you very quickly how it works in the experiment, this is an example of the initial loading. And after the sorting procedure, you see that we have the top part of the array that is very well filled. And again, here I'm showing you a few experimental repetitions where the average filling of this target part of the array is about 99%. So if we repeat the experiment many times, we get to see perfect 300 atom arrays with a few percent probability. Now, this procedure, this sorting procedure is very flexible, and we can use it to rearrange the atoms into different geometries on a 2D plane. So with this, I showed you what is the first key element of the experiment, which is the capability of creating two-dimensional arrays of neutral atoms with programmable geometries. But now, to be able to do some interesting physics here, we would like the atoms to interact strongly with each other. And so to do that, we start with the atoms in a ground state, in an electronic ground state G, and then we use an optical transition to excite them into a Rydberg state. So the idea here is that the Rydberg state is a highly electronic Rydberg state, so its effective size is much larger than the initial one. It's about 1,000 times larger. So when two atoms are in the Rydberg state, they interact with each other through strong van der Waals interactions that scale with the distance, with 1 over the distance to the 6th power. So in this context, there is this, so when the atoms are close to each other, we have this Rydberg blockade mechanism, which simply tells us that if the atoms are within a certain distance from each other, the energy of the doubly excited state is shifted up. so that the simultaneous excitation of both atoms to the Rydberg state is effectively not allowed anymore. And this happens within a certain characteristic length scale that is called the blockade radius. So this gives us the second key ingredient of the experiment, which is the possibility of turning on and off these strong long-range interactions by performing these excitations to the Rydberg state. So here, first of all, I want to show you an example of how we can use this Rydberg blockade mechanism in order to generate interesting quantum many-body phases. And I will take this as a first example, a simple square lattice, where when we turn on this optical transition just by shining lasers onto the atoms, the effective Hamiltonian that describes the system is the following. So we have a driving term proportional to the Rabi frequency of the transition omega, a detuning term where delta is the detuning from the Rydberg state, and finally the interaction between Rydberg atoms. So if we have a blockade radius that covers the 4 nearest neighbors of an atom, so for a Rydberg state, for a Rydberg atom here, its 4 nearest neighbors are all blockaded. They cannot be simultaneously excited. We can ask ourselves, what is the many-body ground state if we have an optical transition with a positive detuning delta? So we want to maximize the number of Rydberg excitations, but we need to respect this constraint that is given by the blockade mechanism. And so the ground state in this case is the antiferromagnetic state where the Rydberg atoms are arranged in this checkerboard pattern. So here the Rydberg atoms are marked by these red circles. So this is a simple example to show you how this simple Rydberg blockade mechanism indeed allow us to access interesting quantum many-body phases. And in this paper that we recently posted on the archive, we showed how we can use this same mechanism to probe the phase diagram of the Rydberg atoms on a square lattice, and also to study the phase transitions into them. And this is related to a similar work that was performed in the Broadway's group in Paris. Finally, we also did a recent work where we studied quantum many-body dynamics in these 2-dimensional arrays related to quantum many-body scars. But today I want to talk to you more in details about the latest experiment on spin liquids. So these quantum spin liquids are a phase of matter that was initially proposed by Philip Anderson about 50 years ago with the first work in the 70s, and where he was considering a system of spin 1/2 particles on a frustrated lattice. So in presence of antiferromagnetic interaction, there is this geometrical frustration, for example, on a triangular lattice. And his proposal was that the spins in the system would form entangled pairs, also called dimers, where the state of the pair would be this EPR state. So his idea was that all the spins in the lattice would form these pairs, these entangled pairs. And you can easily see that there is not a single possibility for the pairings. There are many, there are exponentially many. So the many-body ground state of the system would be the superposition of all the possible dimer coverings that you can build on the lattice. And this is what he called a resonating valence bond state, which corresponds to this quantum spin liquid. Now, since this first proposal, these quantum spin liquids have been intensively studied in the past 50 years, and a number of very exciting properties have come up. So you can easily see that there is no spatial order in this state, but this state has topological order. It has long-range quantum entanglement. It has quasi-particle excitations with anionic statistics. And among the many, I just want to mention that these quantum spin liquids have been proposed as a very interesting candidate to implement robust quantum computation, as it's known from the famous star code model that was proposed by Kitaev. Now, despite the huge interest in these spin liquids and the huge efforts to actually observe these in experiments, there has been no conclusive experimental evidence of this state in any experimental system. So, of course, we were very excited when last year two theoretical groups at Harvard started to look into the possibility of creating spin liquid states using Rydberg atoms. And in these two works that I'm showing here, they demonstrated the possibility of using Rydberg atoms to produce interesting dimer models. And in particular, they showed that it's possible to observe solid and liquid dimer phases in certain types of frustrated lattices. Now, today I'm going to show you the results, the experimental results related to this second model here. So the idea is that we arrange the atoms on a Ruby lattice, which simply corresponds to having the atoms on the links of a Kagome lattice, as you see here. So what we do here is to choose the blockade radius such that for an atom in the Rydberg state here, its 6 nearest neighbors are all blockaded. And this gives a constraint on the maximum density of excitations in the system, which is 1/4. Now, this constraint allows us to map this system onto a dimer model, where basically each Rydberg excitation corresponds to a dimer on the Kagome lattice that connects the two adjacent vertices, as I'm showing here. So this constraint on the density tells us that each vertex here can be touched by a maximum of 1 dimer. And I'm gonna talk a lot about perfect dimer covering. What I mean with a perfect dimer covering is a system with exactly 1/4 filling. So each vertex is touched by exactly 1 dimer. So it was proved in this theoretical work that in this model, there exists a quantum spin liquid state that corresponds to the superposition of all the possible dimer coverings that you can build on this lattice. And so you easily see that this is very similar to the resonating valence bond state that I showed you before that was predicted by Anderson. And this state, and it's also been shown that this state has the 2 topological order. So what we do in the experiment is very similar to what I showed you before for the square lattice. We turn on this excitation to the Rydberg state, and we look at the final state after some time evolution. So here is an example of what we see at the end of the state preparation. And what you see is that we have a quite nice dimer covering, which means that most vertices in the array are touched by exactly 1 dimer. Here, the Rydberg excitations are marked as dimers. And we have a few defects here and there where we have empty vertices. But also you can see that this state seems to have no obvious spatial order. So it looks like a disordered array of Rydberg excitations. But now let's look a little bit more in details how we do the preparation and how we characterize this state. So we perform a quasi-adiabatic state preparation by turning on the Rabi frequency omega of the transition, and then we start with the negative detuning so that all the atoms are initially in the ground state. And then we slowly tune the detuning to positive values to allow for more and more excitations. So at different final detunings, we measure the average density of excitations n. And what we observe is that the density slowly grows and reaches this 1/4 filling that we talked about before for the dimer model. So how can we characterize this state? How do we know if what we have here is indeed a quantum spin liquid? So the thing about these topological phases is that they cannot be simply probed using local observables. So we need to introduce these topological string operators that allow us to probe many body correlations between the atoms on large distances. And this is something that you might be familiar with if you are familiar with the toric code. It's something very similar to what is defined there. So in our case, we have a first string operator Z, that is a diagonal operator, which simply corresponds to measuring the parity of dimers along a string. And this string needs to be perpendicular to the bonds of the Kagome lattice, as I'm showing here. So if we take, for example, this closed loop, that is the smallest closed loop that you can draw in the lattice, which encloses a single vertex, you see that for any dimer covering, for any perfect dimer covering, you will always have a parity of -1 on this loop, because you always have exactly 1 dimer out of the 4 bonds that are crossed by the loop. So if we extend this argument, you will see that for a larger loop, the parity always corresponds to -1 to the number of vertices enclosed by the loop, because for each vertex, you get a -1. So for a perfect dimer covering, we would always measure either +1 or -1 according to the number of vertices inside. If we have some density of defects, of course, the amplitude on average of this signal would be reduced. So what we measure in the experiment is shown here. Here I'm showing the results for these two closed loops. And here you see that for negative detuning, we have a positive average parity, which is a trivial consequence of the fact that the density of excitations is very low. And so most of the times these loops don't cross any dimers, so they give +1. But now when we go to positive detunings, we see that this goes to 0, and then it grows again to a finite value in this range of detunings. And also what we notice here is that the sign of this for the two loops is different. And this is due to the fact that this has 6 vertices inside and this has 11. So this is coming from this rule that we had written down here. So this comes from the fact that they have a different parity of vertices inside. So now if we zoom in this range of detunings and we measure the parity for loops of different sizes, we see that all of these have a finite expectation value and that the sign matches with the parity of vertices inside. Now, these allow us to conclude that we do indeed observe the transition into an approximate dimer phase on this lattice. I guess I have 5 minutes.
You have 5 minutes. I wanted to say that, but you anticipated me.
Okay, perfect. Okay, so at this point, we also want to demonstrate that we have coherence between different dimer coverings, as I said at the beginning, to show that this is a spin liquid. So to do that, we need to measure coherence. We need to introduce a second string operator, which is off diagonal, and it's defined like this. So here we define it with its action on a single triangle of the Kagame lattice. So when we act with X on this side, we're gonna create or annihilate a dimer on that side and swap the position of dimers on the opposite sides. Now, the action of X on a closed loop, what it does is that it maps a valid dimer covering into another dimer covering. So applying X on a closed loop couples different dimer coverings, which means that if we measure a finite expectation value for X on a closed loop, it means that we have coherence between different dimer coverings. And so measuring these closed X loops is the key measurement to prove that we have coherence. Now, the tricky part is how to measure this in the experiment, but I will be quick on this. It was proposed again in this theoretical paper that it's possible to do a basis rotation to transform X into Z by doing a time evolution of the state with a quench Hamiltonian, where we reduce the blockade radius such that it covers only the atoms on the same triangle. So after a certain time tau, so we do this time evolution with this quench Hamiltonian for time tau, and this implements the basis rotation that transforms X into Z. So in the experiment, what we do is that after the state preparation, we quench the detuning or resonance, and we increase the Rabi frequency omega to change the blockade radius. So we first calibrate the time tau for this basis rotation, and then we measure X on loops of different sizes, as I'm showing here. And we do indeed observe a finite expectation value on a broad range of detunings, as I'm showing here. So this tells us that we have indeed some degree of coherence between different dimer coverings. So summarizing these two measurements, we observe from the finite expectation value of Z loops, we know that we are in a dimer phase. From this second measurement of X loops, we know that we have some degree of coherence between dimer coverings. And all of this together tells us that we are observing the onset of a quantum spin liquid phase. And here I just want to point out that the key element here is this ability to measure these string operators that is something that has never been possible before in other experimental systems. So now quickly, I just wanted to show you how we can use this spin liquid to start thinking about how to implement, to create a topological qubit. So to do this, we need a system with non-trivial topology. And so what we do is to add a hole at the center of the array by removing 3 atoms here to create an inner boundary. So in this situation, we are creating 2 distinct topological sectors for the dimer coverings. And you can see this easily if you create the transition graphs between two dimer coverings, as I'm doing here. You basically superimpose the two and you remove the overlapping dimers. And we do the same for this pair. And what you see is that the key difference between these two is that here we have a closed loop of dimers that goes around the hole, which tells you that to transform one into the other, you need to do this large set of non-local moves around the hole to do the transformation. And so this tells us that these belong to opposite topological sectors, whereas these one are in the same. So we can define the logical state as the quantum spin liquids that are superposition of all the dimer coverings in one topological sector or in the other. And then we can define the logical operators, sigma z. So sigma z is any z string that connects the hole with the boundary. And this has a well-defined expectation value for all the states in one sector and the opposite expectation value for the opposite sector. And so it has eigenstates, two logical states with eigenvalues ±1. And then we define sigma x as an x loop that goes around the hole, because this has eigenstates, the symmetric and antisymmetric superposition of 0 and L. Now we can measure this in the experiment. We do the same state preparation as we did before, and we measure these two. Now in the range where we had identified a quantum spin liquid before, we see that sigma z is 0, which means that we have a superposition of the two topological sectors, but sigma x is positive, which means that we are generating a state which has a finite overlap with the plus state. So these are just the very first steps towards the creation of a topological qubit. Of course, there is a lot more to be done. But I also want to point out that there has been a related work on these topological qubits by the Google group that has been recently posted on the archive. So with this, I'm a bit out of time, but so this is a summary of what I showed you so far. But I just want to point out a bit, what are the open questions here? So we know that, I didn't have time to show this, but we know that this is not the ground state of the system that we're preparing. It's some non-equilibrium state. So we need to understand a bit better what is the origin of this state. We would like to improve the state preparation. But most interestingly, we're trying to understand how we can indeed encode both states of the topological qubit, how we can manipulate it and implement gates. And so there is a lot more interesting things coming. So with this, I just want to acknowledge the team that has been working on this. This is the experimental team in the lab, our PIs. And I also want to acknowledge the amazing theoretical operators that have been a big help on this, and in particular, Ruben and Hannes, who has been crucial to the realization of this work. So with this, I will take any questions that you have.